Hi guys, and welcome to Unit 2. In this unit, we're going to start off talking about energy on Earth, and this is coming from Chapter 4 in your textbook, Ecosystems and the Physical Environment. So keep in mind that in AP Environmental Science, we want to keep that attitude of stewardship, where we're basically looking to manage ecosystems. And remember, an ecosystem is all the living or biotic things and non-living factors, abiotic things, in an area and how they work together. So this unit is going to focus more on those abiotic things, all of those components that help the living things survive. And then we'll move on to those biotic components later in the year. These are our major topics this unit. I like to think of this as our earth science unit because that's essentially what it is. The tricky thing about it is we are taking what I would normally teach in a half of a year with earth science and condensing it down into a couple weeks. So we're going to move pretty fast, but you can see these are the topics that we're going to cover here. So we've talked about Earth as a system. And when we're talking about systems, Earth can be thought of in some ways as an open system where things can come in and out, and in some ways as a closed system where nothing's coming in, nothing's going out. So when we're talking about energy, we want to talk about Earth being like an open system. Energy comes in and energy can leave. But later on in our next units, we're going to talk about biomass, all the living things. And we're going to find that these things and a lot of the nutrients and things like that will actually recycle. So in that case, nothing's leaving, nothing's coming in unless you have a rare asteroid that's carrying some unique molecule in. For the most part, nothing's really getting in through our atmosphere or leaving in terms of biomass, in terms of nutrients and other elements and things like that. It's only energy that can get in and out. So that we need to start talking about a couple of fundamental laws here. First one is the first law of thermodynamics, and I like to think about this as the quantity of energy. So this is pretty famous, you've probably heard of it before. It says that energy can change forms, but it can't be created or destroyed. So that means that all the energy in the universe, the total amount has to stay the same. But because we said Earth is an open system, we can actually lose energy from Earth. We just have to make sure that in the universe the total number stays the same. So in the entire universe, again, the energy that we start with is going to be the same as the energy we end with, but it may have changed forms. It might be different types of energy now, but it's the same quantity of energy. So that's what the first law says. The second law, on the other hand, is all about quality of energy. So this is where that type of energy comes in. So the second law of thermodynamics says that entropy, which is chaos or disorder, kind of rules. Everything wants to be chaotic and disorganized. And if you let things go on their own, they will become more and more disorganized. So that's what happens with energy too. You can think about it like if you had a gas and you release a gas in one area of the room, it's going to start to spread throughout the entire room and it's going to end up like this. So it's going to end up more disordered. You might have a nice neat pile of bricks and then, a storm comes along or a person comes along and messes them up. So you're not going to have that nice neat pile anymore. So everything in nature tends to become more disorganized as time goes on, and energy is the same way. We start with really good usable energy, so it has low entropy because it's not disordered. It's really nice and neat and usable. But then as time goes on, that energy becomes less usable because it gets lost. Lots of it gets lost as heat, and heat is not something that our bodies can really use very efficiently. So how does this apply to the environment? Well, if we think about where our energy comes from, most of the energy we're using originally comes from the sun. So that's where the energy is coming into this open system here. And then there's two things that can happen to it, well, more than two things. But basically, it can go back out or it can be used in this system. But I want you to notice that eventually, all the energy going out of the system equals the energy that's coming in. So this is our first law of thermodynamics. We change the type of energy along the way, but it's the same amount that comes in, that goes out, nothing's created, nothing's destroyed. The other thing that I want you to notice is it does change. The type of energy changes as you go along. And a lot of this also changes the quality of that energy. It gets more and more disordered. You can see it was nice and neat, nice pure energy coming in from the sun, and then that disorder, that entropy increases, and lots of this energy is lost as heat or radiation back into space. So at that point, it's very high entropy. It's not very disordered. So that's your second law right there. So our energy is coming from the sun. Some important things to remember is that not everywhere on Earth gets the equal amount of sunlight, so it does depend on where you are. If you look at the shape of the Earth, because of its curvature here, its curved shape, anywhere in that tropical region is pretty much always going to get more sun, more direct sun rays than those polar regions, no matter how it's tilted. Even when the South Pole is tilted towards the sun, it doesn't get as direct rays as those tropical areas. So it's important that you kind of know that pattern. That creates these temperature zones on Earth. Because they're getting more direct sun, they're going to be warmer near the equator. Because it's less direct sunlight, it will be cooler near the poles. A good way to think of this is to think about how a flashlight might hit an area. If you shine the flashlight directly down, which is like when the sun is shining directly at that equator, then it's a very direct light. You're at a 90-degree angle here, so you're taking that light and putting it in one intense small surface area. When you start to angle that flashlight beam away from the surface, it actually covers more area. So the light reaches more places, but because it's spread over a greater area, no one part of this surface is getting as much light here as this area was over here. And again, the greater the angle that you angle that, the more the surface area spreads out, and that means that again the light is going to get less intense. So it's all about the intensity of the solar rays, and you can kind of see that same idea here. Depending where you are on Earth at any given time, it's going to be spread out over different amounts of area, and that's going to change the intensity of the radiation. There are also seasonal changes. So remember that Earth is not straight up and down. It's actually tilted on an axis, and Earth's axis is at a 23.5 degree tilt away from perpendicular, so perpendicular would be straight up and down. And because of that, as we go around the sun, different areas get more direct amounts of sunlight. So this is what happens, is that in March, starting March 21st and going to September 22nd, the northern hemisphere here is more tilted towards the sun. So that's where we are, and that's why we have summer at that time of year, because we're tilted more towards the sun, so we get more direct sunlight, longer days, and things like that. As we go the other direction from September 22nd all the way to March 21st, we are tilted away, and the southern hemisphere is tilted towards the sun. And because of that, they are getting the direct sunlight, and they go into summer at that time. So here's another picture that kind of shows you that. You may want to refamiliarize yourself with those ideas of solstices and equinoxes. Just kind of make sure you have that idea down. Now let's talk about how energy is moved once it's on Earth. So there's three forms that energy can be transferred in. Remember, we said we can't create it, we can't destroy it, but we can transfer it. So it can be conducted, or it can go through a convection current, or it can be radiated outwards. So conduction is basically caused by molecules moving and hitting each other. So if substances are touching each other, if they're in direct contact, then the molecules moving faster will cause the molecules in the other substance to move faster, and that will heat things up. So if you have a hot pan, the molecules in the pan are getting hot and they're moving around really quickly, and they start hitting each other a lot. And then if you touch that handle and it's not insulated in any way, your hand's going to get really hot because your molecules are going to start moving really fast as you touch those molecules. Convection is a little different. This is, you can think of it as circulation. It's an up and down movement. It's a cycle. So this is what's happening inside of that pot of boiling water. The water on the bottom is getting hot, and as it gets hot, it's going to get less dense and it's going to rise, and then the colder water on top is going to be more dense, so it's going to fall, and it's going to create this cycle of hot stuff rising, cold stuff falling. So you can think of it as a current. That's how convection works. And then radiation is our last one, where it moves outwards. And this is how the sun's light is getting to us, because it's moving through these electromagnetic waves. So this would be the stuff coming out from the fire. This can travel through space. The rest of them can't. So this is the only type of energy that you're going to find in space. So another example, conduction would be the heat you feel when you have your hands around a warm cup of coffee. Convection is how your heating system in your house works to circulate air, and radiation would be how your marshmallows are getting toasted without touching the fire. In the environment, here's how this is working. Convection really drives all of our currents, our ocean currents, wind currents, even magma currents under the surface. It causes all the temperature gradients that we see, and because of that, it causes all of our weather and climate patterns. Radiation is how our sun's energy is reaching us, and it's also how it's being lost back as heat to space. And then conduction would be happening anywhere that energy is being absorbed by land, by plants, by the atmosphere, or by any other sort of organism. One thing that's kind of important that we'll come back to many points this year is the greenhouse effect. Basically, that's that we have this sort of blanketed gas around us, CO2, methane, lots of other greenhouse gases, and those absorb heat from the sun and kind of trap it inside and insulate the earth. So this is a problem with global climate change, is we're adding to these gases, we're increasing this insulation, and that increases our temperature. So we want to try to make sure that we kind of have a way to avoid that happening. So if we look at what happens to solar radiation when it comes into Earth, we see that three things are happening. Some of that energy gets absorbed by different things on Earth. Some of it gets transmitted right through something. If it's translucent, that will happen. And some energy can bounce off the object. And that brings us to a topic that we call albedo. So albedo basically means how much energy is being reflected. So the more energy is reflected, the higher the albedo. And a lot of people ask if this is good or bad. Well, it depends. We do want there to be a high albedo most of the time, but it is okay to have a low albedo if that's caused by having plants that are absorbing the light instead of reflecting it. Because they're using it to create sugars. However, if it's being absorbed by something like concrete that's not using it, then it's just going to cause a temperature change, and that of course could only make climate change worse. So naturally, we generally tend to think of things with high albedo as being a good thing. So the Arctic ice, it reflects a lot of light back into space. Deserts, same thing. And that keeps us from heating up too much because it's reflecting back out because of that high albedo. Take a look at this picture. You do need to know these numbers. This is kind of our balance for what we want to happen. Out of our solar radiation that comes in, we want about 31% of it to be reflected, and the other 69% of it to be absorbed. We start to run into problems when we have less being reflected and more being absorbed, because it throws the whole thing out of balance. And this is what we're worried about with albedo and global warming, is that what's happening is that energy is coming in. It used to be reflected by these huge ice packs, but because of global warming, the ice is melted, so it's not reflecting. That high albedo is now gone. It's now a lower albedo, and because of that, it doesn't reflect as much. More is absorbed, and then those greenhouse gases trap everything in too, so it only gets worse and worse and worse. And that's why it's a positive feedback mechanism. As time goes on and more of those icy areas melt, you get lower and lower albedo. I want you to also notice deserts do have high albedo, so they're going to reflect a lot of that light back into space as well. But deserts come with their own set of problems. So this is kind of just a slide that puts everything together that we've talked about. Just come in ready to talk about albedo next class and what's happening with solar radiation once it enters our ecosystem. And then we'll go from there. See you tomorrow.